Hi everyone, so I'm just continuing on from that last lecture, and for anyone else who was at lecture today before the long weekend, this should catch us all up to the syllabus so that we can continue talking about Lewis structures of molecules when we get back on Wednesday. So, we're talking about Lewis structures we started with ionic compounds, we moved into covalent compounds, and we talked about the difference between an unshared electron and a shared electron, right? We're going to build up to an explanation of where this different properties come from, of when two atoms come together, what is going to dictate if they behave like an ionic compound, and what is going to dictate if they behave more like a covalent bond. So the first thing we want to look at is called bond polarity. So we're going to start by talking about covalent bonds. So on the left-hand side of the screen, we have molecular chlorine, so that's Cl2. Each of them are sharing one electron together, and that electron wave function is now part of the molecule. And so if we look at chlorine, if we think about in the middle here, if we take it a more basic approach to understanding what's happening, if we just concentrate on these two electrons, rather than it being a wave function over the entirety of the molecule, we can see that there's going to be a tug of war between this chlorine and that chlorine. What ends up happening, so since they're both chlorine, it's like having tug of war with your identical twin. You're both pulling in opposite directions, but no one's moving anywhere. And so this is what we call a non-polar bond. You don't necessarily need to be identically the same atom, so in this case like chlorine, but you can have atoms that have similar pulls. So it's like having a tug of war against someone who's of similar strength than you, though not necessarily your clone. So this is what we call a non-polar bond, where there really is no one-sidedness between the pull on the electrons, and what you see here is this pretty symmetrical distribution of electron density around the entirety of the molecule. On the other hand, you can have a polar bond, and so this is like our last example of talking about hydrochloric acid. So we're going to compare the polarity, so the relative strength at which each atom is pulling on the other electrons. So again, for the time being, we're going to forget about the idea of the wave function being the electrons are distributed through the entire molecule, but instead we think about these two bonding electrons and their relative pull towards the H or the Cl. We'll learn shortly that Cl ends up having a much stronger pull towards electrons than the hydrogen, and this does track with electron affinity. And so what ends up happening is it's an uneven sharing of electrons, and it's pulling more towards the chlorine. If we think about that in terms of the electron density, so again of the wave function, and this is what you see on this heat map, it's the idea on the blue side, you're pulling more electron density towards the chlorine. So it's an oblong, it's a not an oblong shape, but an asymmetrical shape. So a lot of the electron density is over here by the chlorine, and less of the electron density is around the hydrogen. So what you see here are two particular symbols. So again, we're reaching into the Greek alphabet. So over here, because we have a higher concentration of electrons, it's not a full additional negative charge like when we had a chlorine minus in the sense of sodium chloride. Here it has a partial negative charge. So it's not saying it's a full negative charge, but it is recognizing that there is this asymmetric distribution of electron density around the molecule. The way we represent that is by this symbol here. So this is the Greek letter lowercase delta. So before we use uppercase delta, which is the triangle. This is the lowercase delta, which is like the fancy looking D. So we have delta minus, so it's a partial negative charge on the chlorine, and because it's part of the same molecule, it means on the other side, as we have this deficiency of electron density, we have this partial positive charge, or delta positive. Again, first slide's always tough to change for some reason. There we go. All right. So what we want to talk about is, why does this arise? Why did the Cl2 end up having this non-polar bond, but this HCl has a polar bond? Right? So we bring up this concept called electronegativity. So that's the measure of the ability of an atom in a molecule to draw electrons to itself, specifically bonding electrons. So again, we're not talking about the core electrons, we are talking about the valence shell electrons. So electronegativity, it is a useful quantitative way to compare how much an atom is going to pull electrons towards itself. It's actually not a real quantity. It arises from differences in quantum mechanics, which we'll talk about later when we get to molecular orbital theory. But for right now, we're just going to talk about it as electronegativity. So certain molecules are more electronegative, which means they pull in bonding electrons towards themselves. And Cl is one of the most electronegative atoms on the periodic table. And compared to hydrogen, it's much more electronegative. So therefore, it's going to start pulling that electron density towards itself unevenly. So the way we represent that is that we can draw the H. There's our bonding electrons to Cl. So we have a partial positive, partial negative. In a way that is more often represented is using a vector, which is saying that H and the electrons are being pulled towards the Cl. So there we have our arrow pointing, or a vector pointing towards chlorine. And then we put a hash mark at the end, the other side, which this denotes the positive, partial positive charge. So we have one more trend to, or at least another trend to start to recognize when looking at the periodic table. In general, again, there's always exceptions to the rule, but in general, you go from the least electronegative, which is cesium, which has a value of 0.7, all the way up to fluorine, which has a value of 4.0. So fluorine is the most electronegative element. And so actually, it's interesting, if you look at how pharmaceutical companies modify certain drugs, they use fluorine a lot instead of hydrogen to change the electron density in certain molecules to help make them become better drugs, that they bind better to proteins or to molecules to have a biological effect. This scale is, as far as I can tell, is pretty arbitrary. It was designed by Linus Pauling. I don't know what it's based off of, but all scales of electronegativity, there's other scales, but all of them can be brought back to this scale. So it's just a relative number. There is it doesn't have some real physical meaning of 4 and 0.7, but they're relative numbers to each other. So if we're talking about relative electronegativity, which you can see here, it's represented down on the bottom is kind of through the size of the vector. And we see as we go across the periodic table, if we're up here, we see carbon, nitrogen, oxygen, fluorine. We're going up in negativity, in electronegativity. That's what's being compared here. So when you have carbon-carbon, again, we think of this as tug of war between those bonding electrons. So what ends up happening is it's equal. So there's nonpolar. And then if we go back again, we see we're comparing carbon and nitrogen here. So it's a little bit more polar. The electron density is being pulled towards the nitrogen. So again, the vector is pointing towards the more electronegative element of nitrogen. We represent that by delta minus and a delta plus on the carbon. Again, now we're comparing carbon to oxygen. Same thing here. That vector got a little bit bigger because we're getting the electron density is being pulled more toward the oxygen. And then finally, we have a carbon-fluorine bond, and you can see the vector has become larger, and we're pulling that more towards the fluorine again. The way we look at these differences is by directly comparing these values for electronegativity of 2.5, 3, 3.5, and 4. So when we looked at electronegativity difference, we have two carbons. Each of them is 2.5. 2.5 minus 2.5 is 0, therefore it's nonpolar. We look at the difference between carbon and nitrogen. 3 minus 2.5 is a half of an electronegativity unit, which is usually called a poly. Again, we go for carbon to oxygen, it gets bigger, it's 1. And again, we look at the difference between fluorine and carbon, it's even larger, more. So we get more and more polar, right? And so this is kind of just putting this on a continuum. Again, this is kind of just a rough estimate. There's going to be compounds that are in between ionic and covalent bonds. There are going to be compounds between nonpolar and polar, right? It's kind of like when we were talking about the difference between metalloids and metals and non-ionics, right? We have those compounds or those atoms that make that stepwise shape on the left-hand or the right-hand side of the periodic table, where they both have kind of properties of metals, kind of properties of non-metals. So it's always acting on a continuum, and that's what we see here. So the non-polar covalent is when we look at that difference between electronegativity numbers, and it's roughly between 0 and 0.5. As you approach 0.5, it kind of becomes ambiguous if it's going to be non-polar and a covalent bond. As we get somewhere in the middle, right, we have electronegativity between 0.5 and 2.1. This is where it is shared, but it's a little bit unevenly shared, right? We had the hydrochloric acid as our example, where the chlorine is more electronegative, so that that electron distribution it's a little bit more heavy on the chlorine side, so the wave function is more like chlorine than hydrogen. And then we go to the extreme. So this is where we have our ionic bonding, where we exceed this electronegativity difference of 2.1, and after that, that's when it becomes completely unevenly shared, just like when we look at sodium chloride. At beyond electronegativity difference of 2.1, the electron itself is completely donated to the anion, and the cation and the anion are held together now by that electrostatic force that we talked about in the last lecture. So I think we are stopping here. So this is more of a preview of where we're going to be going next time in terms of putting together our Lewis structures into covalent molecules. It will help us to decide what the shape of the molecule is going to be and the polarity of the molecule. Once we can put this together to construct molecule shapes based on the Lewis structure, and then what we'll do is we'll apply our electronegativity rules to figure out if molecules are polar or not. So this is where we're going to pick up on Wednesday. I hope you guys all enjoy the long weekend. It's beautiful out right now. I know it's supposed to be a little bit nasty tomorrow on Saturday, but spring is finally feel like it's here. So, all right, enjoy the weekend. I will see you all on Wednesday.